This short little video is to talk about conditional convergence. All right, so what does it mean for a series to conditionally converge? Well, the answer is it's conditionally convergent if it is convergent, but not absolutely convergent. Remember, if it's absolutely convergent, then it necessarily converges. But it's not true that just because it converges, it has to be absolutely convergent. So those series that converge but do not converge absolutely, we say are conditionally convergent, or equivalently converges conditionally. All right, so let's look at a few examples. Here's the first example. Summation, n running from 1 to infinity of minus 1 to the n. We've already seen this series before when we were looking at the alternating series test, I think. The point is, this series converges by the alternating series test. Remember the alternating series test, terms have to be decreasing, greater than 0, and a sub n plus 1 has to be less than or equal to a sub n. Well, all of that fits. So the alternating series test says that this series converges. Now, but if I look at the series of absolute values, which means I take the absolute value of this, which means minus 1 to the n goes away, then what I'm looking at is the series 1 over n. Well, you should realize that the series 1 over n does what? Diverges y, because it's the harmonic series, or another way of thinking about it is it's a p series with p equal 1. So there you have an example of a series that converges but does not converge absolutely. Why? Because the series of absolute values diverges. All right, let's look at another example. N running from 2 to infinity, minus 1 to the n over n log n. Again, I claim that if you run the alternating series test on it, that it converges. But if you look at its series of absolute values, which is the summation 2 running from 1 to infinity of 1 over n log n, I claim that that diverges. And what test am I using? I'm using the integral test, which means what? I'm going to integrate from 2 to infinity of 1 over x log x. And if you think about it, you should be able to integrate that with 1 u substitution. All right. Our final example is n running from 1 to infinity, minus 1 to the n over the square root of n. All right. Again, I claim that if you run the alternating series test, because it is an alternating series, that you're going to get this thing converges. But if you look at the series of absolute values, then you're looking at the summation n running from 1 to infinity of 1 over the square root of n. Well, the square root of n is really n to the 1/2. And so 1 over the square root of n is a p series. It looks like 1 over n to the p, where p is equal to what? 1/2. And what's the point? 1/2 is less than 1. So that series diverges. Okay, so there's the third example of a series that converges, but it diverges absolutely, right? Which means all of these are examples of series that are what? Conditionally convergent. Which again means they converge, but they do not converge absolutely. So I think that's all I have to say about this. Bye.